Hello and welcome to the Web Application Hacking 104 and Exploit Development 104 lectures. My name is Dr. Owen Redwood, and this lecture is part of the Offensive Computer Security 2.0 OpenCourseWare, brought to you by hackallthethings.com. Today's outline, we're going to cover IDS and IPS systems, web application firewalls, and how to defeat these defensive systems. By now, you should understand the primary differences between web application hacking or web exploitation versus binary exploitation. Connect back shellcode and more advanced shellcode development, including coded and polymorphic shellcode, will be covered in depth at the end of the lecture, as they relate heavily to defeating IDS and IPS systems for exploiting binary exploitation vulnerabilities. Um, some of these techniques do not apply to web application exploitation, so keep that in mind. So, intrusion detection and prevention systems primarily operate at the transport and network layers. Web application firewalls typically operate at the application layer. You will usually see IDSs and IPSs just stick to transport network. I guess there's nothing preventing some advanced ones or some fancy ones from doing anything in the application layer. However, it depends on the application itself. There are tons of applications out there ranging from web servers to LDAP services to databases, etc., etc., etc. The goal of the network and transport layer is to monitor for malicious activity and potential policy violations. This all gets reported up to the system administration group or the incident response group. And usually the scope of what it analyzes is a packet by packet basis. It doesn't always have the capability to analyze an entire stream of data or entire file being sent from one application to another, for instance, from a web server to your browser. Now, IDSs and IPSs that have that technology to be able to piece things back together do something called stateful packet inspection. And at its core, stateful packet inspection is primarily just for monitoring TCP sessions for anomalies for perhaps protocol noncompliance, monitoring UDP sessions, or rather just flows, for anomalies and signs of attacks. For TCP, since the flows go back each way and there's a handshake, the flow is really just one way. For TCP, the stateful packet inspection begins on each SYN packet. Now, keeping track of each session takes memory, and so there's an overhead for tracking each session. Perhaps this can be exhausted to degrade the performance of an IDS system. It depends on the implementation, obviously. But at its core, this technology allows the defenders to prevent certain kind of attacks, especially denial of service attacks that cause a network stack to slow down or perhaps crash on malformed packets or packets that don't comply with the protocol. For instance, this is a sample diagram, there are many like it, of TCP state transitions. Each, I guess, square you would see as a group of states, and each circle would be a state in itself, and there's transitions dictating what messages occur in order to transition from one state to another. So, for instance, if a session tries sending a receive fin packet right after listen or receive send, the IDS using stateful packet inspection would be able to detect that anomaly, as there's not a normal transition for that packet. And if that's actually an attack, it may cause the receiving service to slow down and think, why did this happen? and then formulate a packet, say, TCP reset, this packet was sent erroneously. So, which leads us to deep packet inspection, which allows the defender the ability to reconstitute the stream for, say, a TCP session or perhaps a UDP session. It uses stateful packet inspection as well as the ability, since you're already tracking that session, to piece back the data itself that's being sent at the application layers. This allows you to detect things like viruses, spam worms, and even intrusions themselves, as well as exfiltration of data if the attack is unsophisticated. It's commonly used in enterprises and corporate settings and mid-sized businesses, definitely at the internet service provider level. That is effectively their bread and butter in their toolkit, rather. And governments around the world use this technology for all forms of, I guess, legitimate things, as well as censorship, depending on the part of the world you're from. And deep packet inspection, since you can reconstitute the upper level application data that's being sent from one client to a server or vice versa, allows you to do complete eavesdropping, allows you to do data mining, and since it's originally designed to look for keywords or signatures at the application layer that might be indicative of a known attack on, say, a known vulnerability. Since you're already looking at keywords, you can establish bad keywords you don't want and kill the traffic. It's very simple censorship feature. So the point of deep packet inspection is it combines stateful packet inspection with firewall and IDS and IPS. And all these technologies, however, are very trivially defeated usually by any form of compression, such as just regular zip, tar, GZ, bzip, you name it. Any form of encoding, you combine compression with encoding, you've defeated IDSs, IPSs with all the technology in the world combined. Encryption outright defeats them. Tunneling, sometimes it depends on how it's all done, as obviously as well as the encryption. And IDSs are primarily focused on identifying possible incidents. There's some false positives in the mix. And its job is to simply just log all the info about them so that there's an incident, there's a forensics log of what happened on the network and highlighting exactly what packets may have been signs of the attack or leading up to the attack. As a secondary use, IDSs are very commonly used to detect whether systems are misconfigured. Out of the box, most IDS systems are configured to detect common misconfigurations of routers, of web applications, and etc. As well as IDSs provide automated documentation of existing threats and existing attacks on the network. They do deter some threats, insider threats. That bullet point is a little old. I wouldn't talk much about that. Intrusion prevention systems simply are just an IDS system with rules on when certain criteria are met or when certain rules are met, trigger this countermeasure. And the countermeasure is usually to kill the traffic or to block the IP or to ban the subdomain of, say, known malware or something looking like malware. And this can be URL requests to just IP addresses, as well as updating a firewall to block a certain range of ports from now on. It depends. It's obviously left up to implementation in many cases. There are two types of systems here for intrusion detection systems and intrusion prevention systems. And there are network-based ones and there's host-based ones. The network intrusion detection systems, sometimes just called NIDS, are independent platforms. They're supposed to be standalone boxes on your network that have an ability to monitor everything, and usually that's in the form of a natural choke point on your network. Have the ability to view all the traffic incoming from multiple hosts and outgoing from multiple hosts, and perform some sort of analysis on it. And we'll get into that in the next slide. Host-based intrusion detection systems are effectively things like operating system level applications that have the ability to view all the network traffic incoming and outgoing from the host and allow you to do this on a single node basis. Obviously, the host-based intrusion detection system for one system won't see traffic from another system unless it's talking to it. And there are hybrid systems and other systems that are, I guess, less common. Now, as for the types of analysis that these systems can perform automatically, there's the obvious signature-based detection, these series of packets with this payload represents an attack and log it or kill it. And then there's also anomaly-based detections, and the two worth talking about are statistical-based anomaly detection and then also specification-based. Specification-based is summed up best by, if you have a rule, you might have a rule saying if the amount of peer-to-peer traffic exceeds 10% of all the traffic on the network, log that event or take this action. Now, statistical anomaly-based detection without the specification would simply determine the normal behavior of the network, normal levels of bandwidth for various protocols, and traffic going across various ports, and identify the common connections that are made across the day, and then generate alerts when anomalies occur. Perhaps these baselines deviates past a threshold, and then in those cases the operators want to know of those anomalies when they occur in real time, or at least have a log of them. So these can be interfaced or can trigger various tools, including there's a common body, there's a body of research into moving targets, and that if you detect an attack, your DHCP server for your network can reassign everyone's IP address. Say, for instance, there's a probing attack, and someone gets inside your network, and the first thing they do is nmap the whole network to find out what's there. Well, if your network intrusion detection system detects this style of probing attack, perhaps it can trigger the DHCP server to bump everyone's IP address and reassign it randomly. It might deter an attacker or at least slow them down significantly. It may also allow, obviously, reconfiguring the firewall. We've already talked about that. May have feeds into it from honeypots. Now, honeypots offer a great advantage in terms of intrusion detection system. Honeypots have no value in a production environment, and you can tell your employees to avoid communicating with this IP and obviously keep that information confidential so that when an attacker comes in and they start nmapping your network, they can see all the hosts. You may have your honeypot set up with some vulnerable services, and the attacker may go for that first. And if the attacker does go for that first, the thing about honeypots is since no traffic to it is legitimate, any traffic to it at that level would immediately be worthy of generating a flag to alert intrusion detection, alert the incident response team. And some people think that, oh my God, honeypots are a bad thing to have because they're designed to get attacked. Well, if you have them inside your network, behind all your defenses, you'll know when attackers have gotten inside your network and are actively attacking things, as well as perhaps the dumb employee who's misconfigured something and is having their services talk to the wrong IPs. So it's useful in two ways. Um, there's also security environment modifiers. If, say, for instance, intrusion prevention system, these are mostly academic things that trigger different threat levels, and each threat level uh, enacts perhaps the more strict policies than the last one. Um, in practice, I've never seen them. They seem to be an interesting class of research, but at the end of the day, I've spent a lot of time looking into this field, and I always find ways to subvert the system against itself by using very trivial attacks to increase the threat level from one to the next, to the next, to the next, till the system's fully locked down. And what you've done is basically denied a denial of service attack using its own security mechanisms. So, in theory, it could do security environment modifying, um, but yeah. Lastly, web application firewalls occur usually at the application layer. It's commonly called a security appliance. I don't really like that word, but also called a server plugin that basically filters out common categories of attacks. And it basically applies a set of rules to HTTP conversations going to that server, and is designed to prevent cross-site scripting, cross-site request forgery, cross-site blank attacks, SQL injection, and it can be very effective at mitigating most attacks, and is often a requirement for certain industries that are subject to government regulations. Um, yes, this slide is out of order, but regulations in many industries mandate that your company do one of the two. Either you do regular code audits of your software and all the code that you write to get rid of bugs. So that means weekly, bi-weekly engineering meetings where you're poring over your source code, looking for bugs, which an hour every week of, say, 12 or 7 to 12 engineers may cost a lot of money compared to simply buying a web application firewall, setting up some sort of intrusion detection system, probably Snort, and then you don't have to do the weekly code auditing. Now, obviously the code auditing is going to get rid of vulnerabilities in your application, all the code that you write. But if you put up the web application firewall and the IDS, you'll comply with the regulations. So that's the cheaper way out, more often than not. And it actually doesn't have any impact on the number of vulnerabilities that you have in your code. In fact, it often means that the developers don't budget time to do security audits on their code, and vulnerabilities get left in their web applications and never get dealt with. Their ass is covered legally because they've complied with the regulations, regardless of whether they did any security audits. They met one of the two mandates, and that was sufficient. So in practice, I've talked to dozens of pen testers, and they found that if a target is behind a web application firewall, it's not likely code audited, and it's likely to have more vulnerabilities than the other targets on the network, which is just an interesting phenomenon on how this all played out. And one of my friends asked me, I constantly complain about how cyber law is so far behind the times. And he asked me a good question. Do you really want the laws to catch up? Because they don't always get implemented right. And this is one of those cases that they didn't implement it right. And it's driving the overall field to be more insecure, because by giving them this way out, they're not doing anything to actually reduce the number of vulnerabilities in their software. And the web application firewalls and IDS systems aren't perfect. Even if they caught 99% of all the attacks, servers get attacked thousands of times a day. Until you get 6 figures deep in your attack percent deterred or detected rating, you don't have any real security. So until you have 99.99999% attacks detected and deterred, you're not going to have real security. And if you're not reducing the vulnerabilities in your code, that is just an ever-growing target as long as you're writing more and more lines of code on it. So, like I said, the web application firewall lives at the application layer, and it's just designed to do basic sanity checking on your data, provide very few false positives on its detection, and I'm going to pull up OWASP because it's the best resource on it at the moment. When selecting web application firewall, it must cover all of the top 10 all the top 10 attacks that OWASP dictates. OWASP is really probably the de facto standard here on information regarding web application security and hacking. It must, out of the box, be ready to go. It must have default settings that provide strong defenses because more often than not, they're just going to get it up and running and consider the job done. It must be easy to learn to configure it and to do advanced things with the web application firewall. And this has to do more with data leak prevention, detecting outbound messages containing data that looks like credit card numbers and social security numbers. However, nothing's preventing the attackers from exfiltrating that data in a coded or encrypted or compressed fashion. That form of exfiltration is usually impossible to stop. And that's one of the advantages attackers always have, is that they can use these things that we use on defense, such as encryption, to beat our ways of beating them. And I don't think that will ever change. So the list goes on and on and on. And getting back to the lecture, I'll turn to full screen. So web application firewalls often impose restrictions on the various inputs to a form that's being processed by a web server. For instance, a form will usually have some text fields and some number fields, and when configured properly, or perhaps it just learns this automatically, it will filter out all non-ASCII input for string fields and filter out input that doesn't seem like valid numerical input for number fields, and etc. And this style of filtering actually mitigates many attacks. If you've already noticed, the shellcode that we've been exploring when it gets rendered down to the raw byte encoding is actually mostly not ASCII. If you were to map it to the 2E through 7F range, there's actually a very large set of ranges outside of that that is not ASCII and will often occur in shellcode, especially when you're dealing with any form of setting up registers to contain very specific data. Usually if you're trying to, for instance, specify memory addresses, that's not going to play out as valid ASCII bytes. So this actually mitigates many attacks, and there is a way around this mitigation. It's in the form of polymorphic shellcode and encoding, and we'll get into that at the end of this lecture. So we're going to talk now about bypassing intrusion detection systems and prevention systems, and then finally web application firewalls. We're going to revisit the shellcode lectures. So we talked about port binding shellcode and discussed how it's easily foiled by firewalls and easily foiled by NATs. And the way around that for attackers is to have the victim, once the exploit is successful, connect back to the attacker. And outbound connections from hosts inside a network are usually not limited or filtered by a firewall. And this often can defeat intrusion detection systems, prevention systems. Web application firewalls don't really concern themselves with the connection the network and transport layer activities. Um, so in order for this to work, an attacker obviously has to have a listener waiting on one of their nodes in their network, and that may be part of a botnet, or it may be at a VPS that they've anonymously purchased, or it may be their laptop at a Wi-Fi hotspot at a cafe. There's an asymmetric advantage here. The attacker can never disclose his actual identity or location, despite the fact you're having the victim connect back to the attacker. Nonetheless, well, I'll save the rest of that story for later lecture. So, according to the Shellcoder's Handbook, shellcode that does port binding and network connection wasn't introduced to the public until 2005. Now, I want to note that the Morris worm back in 1988 did spread over networks, found a target, infected the target, and then looked in the target's neighborhood in the network and kept spreading and spreading and spreading. But in 2005, there's a Black Hat presentation by Michael Lin on Cisco iOS, which is an operating system that runs on many of their switches and routers. And he demonstrated a port binding shell exploit, and it actually was squashed. The vendors, Cisco and ISS, actually censored the talk and then never published any of the details of the talk. This is noteworthy because Cisco iOS doesn't implement system calls like Linux does. So this required some expert level reverse engineering to figure out how to set this all up. And the iOS system is not well documented. So it was very impressive knowledge and also very dangerous technique at the time. According to my research about a year ago, I haven't picked up the task of looking into this better. Networking shellcode and how-to tutorials on how to write shellcode that does any form of networking didn't really surface on the internet and on the underground until about 2004. There was a frac article, and I've linked it for you if you want to go look at it, on how to do this stuff. Now, there's nothing preventing someone with assembly level experience and networking experience at that level from doing this themselves. So at the public level, this perhaps wasn't known before that, but nothing stopped hackers from doing this if they are sufficiently knowledgeable. So the two components of connect back shellcode are really just a listener on your machine as the attacker, and the exploit code, that the payload, that when you tie the exploit to point to it and you land it, the victim machine will open a port, connect back, and provide shell access. So in essence, if the target is behind a firewall, behind intrusion detection system, the attacker will have to go in over one of the ports that the defenses let into the network. For instance, a web server, you're going to have port 80 coming in, and you're going to have to go over that as the attacker. That's where your web application hacking techniques will come in. Perhaps you just upload a shell and toy around with it. Maybe there's an exploit you have in the web server itself. And let's talk about that later case. The firewall would allow the traffic. The IDS wouldn't notice if it doesn't violate any policies and doesn't match any signature. You may be able to just alter the signature by adding knocks in randomly, and that may be sufficient to throw off dumb signature-based detection systems. And then what would happen is, once the exploit is landed, the target would attempt to connect back to the IP and port specified by the attacker, and the firewall would allow the outbound traffic. And the IDS would only notice if the outbound traffic violated some form of policy, or if a signature was detected, or signature was triggered on the outbound traffic. So intrusion prevention system is very much the same, but if it any point triggers a signature, it may kill the traffic at that stage. So there are many forms of performing a connect back payload, and you can do it with Unix commands like netcat. It's a common Unix tool to do this. And netcat flags V stands for verbose, L tells it to listen, and P specifies the port. E specifies what to execute. So if you have the ability to inject system commands to a target web application, you can tell it to spawn binsh and tie its input and output back to the attacker. Now there are some cheat sheets that I guess are worth looking at, and obviously there's other languages that web applications are written in other than C, such as Perl, and Python is actually increasingly common nowadays. And you'd think that the shell code at this level is still called shell code. You'd think that the exploit code for having a payload just spawn a shell and connecting it back to the attacker in Python would be something like one line, right? Actually, not really. So for each of these, I've listed basically the steps that you take to take this and direct it back to any arbitrary IP address. And that's how most payloads work in the security field. You don't need to have a whole lot of experience writing payloads, and you don't need to be a master ninja at that stuff. There's whole repositories of shellcode and different payloads out there. There's Shellstorm, there's ExploitDB, and there's other ones for PHP, Ruby. Between Shellstorm and ExploitDB, you'll find something for any given target platform, from web application languages all the way down to the binary stuff we're used to. We're going to explore how to write connect back shellcode, working from the previous port binding shellcode example that we had. And we're going to first go over a refresher. Yeah, get that. So this C code effectively binds a socket to an IP address and port, and then it listens for connections, and then handles them after accepting each connection. So if you recall, the socket call library is much different from the way system calls work, and much different from the feature of system calls. In fact, socket calls are a subset of everything that you can do with system calls. So socket calls are just socket system calls, and we went over the list of different functions it provides, and we explored using bind, listen, and accept. And we're going to have to look at connect now. But to continue on the recap, we're going to have to specify when we're making the system call that we're going to use socket call. So EAX will be occupied telling system call to pass the rest of the data to the socket call handler. And EVX will specify what function inside of the socket call handler to actually trigger. Then the ECX will be the start of the arguments for the particular socket call. Usually it's a pointer to a array of arguments. So it's pretty simple, but some parts get tricky. I swear no matter how many times I click that button, it always still comes up. And what we explored was how to translate things, well, highlighted in red and circled properly, into actual shellcode. And the rest of it is just setting up this code, and we just focus on this, and we're able to get that working. So the disassembly view for this line of code effectively moves first on the stack 0, then 1, then 2, then calls the socket function. Could be that EAX was set up and then and that it pointed to the socket system call. So it would be 102 in EAX, and then going back to this function, the syssocket to create a socket would be stored in EBX, so that would be 1, and then ECX would point to the stack pointer, and that's where this array of variables would be to call effectively socket. Instead, what the compiler has done in this little example is that there's the PLT, and what we covered also is the global offset table. The PLT is very similar to it. It provides a table of functions. Some of these are functions that simplify the programmer's job and simplify the compiler's job of calling these operating system level features. And sockets in the PLT just happens to be one of those. That's why you see call socket instead of EAX, EBX, and ECX being set up to call the system call, which calls the socket call, which in fact calls syssocket. Obviously, this is not so verbose and easier to understand. So, going forward, as I said, the arguments are pushed on the stack in reverse order, and this is the cdecl calling convention. In the next lecture, we're going to go back, revisit the calling convention debate topics, and cover cdecl, standard call, and fast call, because the calling conventions are still very, very important, especially for attackers in order to pull off return-oriented programming exploits. So the assembly for the next line of code was simply just move onto the stack, and this -40 is calculated by the size of the other things, and this is all leading up to the eventual call here, passing in this struct effectively. So AFINet is 2, so it's moving 2 into its appropriate place in the struct, and host to network short will translate the given short to the network byte order, so little endian versus big endian, whichever the network has agreed to use, and that is then getting put well, the return value for that will be put in EAX, so that should be then moved. Oh, this got messed up. The result for this line of code should not be truncated there. It should be move dword pointer bracket ESP -38 colon EAX. That's what it should be if I judge that correctly, because the short is going to be 2 bytes, I think. That's assuming 32-bit integers. So, in adder any is a macro in C that specifies it's going to bind to the address 0.0.0.0. So it's going to, as long as the port matches for the incoming traffic, read the traffic and handle the traffic, regardless of whether or not it has the proper IP address for the destination. If it managed to get to the service, or rather to the host, it's going to handle it. So the problem there with the shellcode is that if this is in a buffer overflow exploit, that's a lot of null bytes. So that has to be set up, and obviously the mem set got overlooked because all it's doing is zeroing out the other field, well, the other fields, which is the rest of the struct. And here you see the AF INET is this short, this 2 bytes, and then the 31337, once it's calculated by host to network short, is stored in little endian format here, which I believe 31337 is 697A, but I may be wrong. I can't do this off the top of my head. And then the IP address for in at or any is 0.0.0.0, and then the rest of it is zeroed out. The rest of it actually, in practice, doesn't really matter. And there are ways to make it work like that. So, yep, just said that. Oh, and I was right. And this is the IP address. And these arrows, if they align right, indicate what is what in the overall struct and the higher level view. And as you see, in memory, there's no delimiters separating each byte. It really comes back to memory alignment, and the compiler puts things in their place, and the compiler spews out code that reads things properly and doesn't mess up how the places are tracked. It just works by things should be aligned like this, and then when you're writing it, write it that way, and when you're reading it, read it in the same order. So this is still all recap, but it's good knowledge to review because the midterm is next week. And we're going to have to not learn how to bind, listen, and accept. We're going to have to learn how to instead connect back. So the shellcode to do bind, listen, and accept is actually going to be much longer than what we're going to go for, is just to connect back. So don't panic, it's not actually getting more complicated. So we're going to be changing, instead of bind, listen, accept, to connect here at the higher level. And all this shellcode, this highlighted blue, sets up the sys socket call to establish the socket. And then this sets up the bind, the socket, to the established sock adder struct that specifies the IP address, which was any IP address, the port, and then the internet family. And this shellcode simply just sets up the socket call for listen. So as you see, Intel 80 is called yet again, and ECX is set to point to the stack, and the stack is where the arguments are, and it's pretty straightforward. And again, this is all a refresher. And again, ECX is pointing to the stack. The stack has the socket len, socket adder, and socket file descriptor in that struct. And that's all being passed to the accept socket call. And at the end of the day, that shellcode binds to port 31337 and waits for incoming connections. But it doesn't do anything more than that. Once a attacker connects back to it, it actually doesn't provide them a shell. There's a little more to do there. So this has all just been a very toy example that doesn't do anything out of the box. So now we have to talk about dupe 2 and how to reuse the existing standard in, standard out, and standard error file descriptors to tie the network traffic to a shell and spawn it and get it all working nice and easy like. So dupe 2 is a system call, and a family of system calls. There's dupe 2, there's dupe 3. Dupe 2 is really the useful one here. You give it the old file descriptor and the new file descriptor, and it's going to tie the two of them basically together. So in order to get all the bind, listen, and now accept shell code to actually spawn a shell, what we're going to have to do is use dupe2. We're going to call it 3 times, and we're going to call on the new socket file descriptor this return from accept. So intox80 EAX is going to be populated with the return value for this, which is going to be an integer, which is going to designate the socket file descriptor, which is then, in this shellcode, we put it into EBX. And to call the system call, the EAX has to specify what system call to use. EBX is the first argument, and ECX is the next argument. So this line of code, push just the byte 3F onto the stack and then pop it, is a fancy way of getting around the null bytes that might occur and just move EAX comma byte 3F. Would probably have a lot of null bytes. And this lets you then specify the dupe2 system call. Then what we do is we XOR out ECX. We do dupe the new socket file descriptor and then standard in. Oops, and oh, this slide's better. And then we don't care about the return value for the socket call, the system call, sorry. But it is going to perhaps trash EAX, so we move into the lower half of EAX the byte again, and regardless of whatever is returned by the system call here, it's going to be some form of error code that's going to be pretty low, and the numbers is going to range over. And anyway it plays out, the upper 3 bytes of the 4-byte integer is going to be zeroed out. So since we don't care about it, we just make sure that it's still indicating to use the system call number 63, which is dupe2, and we now want to call dupe2 our socket 1 to specify standard out. So ECX should not have been moved, so we increment it once, and EBX is still pointing to our accept, our socket resulting from accept here. And so EBX never gets messed with by the system calls we're calling, and so we just have to increment ECX, we have to reset EAX, and then we can call it again, and then we do it again, and just increment ECX yet again to B2, and then it's done. The result of this is that the standard in, standard out, and standard error of this process are now tied to the input-output of the socket. So when we go about, this is assuming, your understanding here is, I'm assuming that you've taken operating systems level class, so this is not foreign knowledge. And if you haven't, you just have to accept this is how it works in Linux land. So now that you have the standard in, standard out, and standard error file descriptors set up to point to the socket, when you exec any command, such as exec-ve bin-sh, it's going to spawn that process, but tie that process's standard in, out, and error to the file descriptors that you've set up. It's going to tie it all to the input and output coming in over the socket. So this is all still just port binding shellcode and picking up the previous discussion. So this exec-ve shellcode is nothing new. It's just setting up a string and then in a position independent manner, passing all the arguments to exec.ve system call, and then once intox 80 is called, the payload is in effect. So there are ways to tidy up shellcode, especially since you saw there's some how do you say, repetitive code here. There's patterns going on here. You can make this a little bit more concise with loops and conditional structures, and this code, these 4 bytes, these 4 instructions, actually perform everything that's being done here. And these upper 3 instructions provide all the setup for this. So exchange basically swaps the values of EAX and EBX, and EAX is populated with the return value from accept, and that's going to be the file descriptor, so we're putting that in EBX. And I'm assuming EBX at that time was set to the appropriate value we want to now be designating with our system call when we do intox 80. Or no, I'm sorry. We know what it is. It's 5, and the important part is that the upper bytes were all zeroed out, and we're going to push this 3F byte into it to make EAX be 63 to specify the due to system call. So as for ECX, we're going to, instead of start with 0 and then 1 and then 2, there are a lot of conditional jumps on whether or not something is equal to 0, or whether or not something is not negative or not signed, or etc. And by starting at 2, we can exploit those, or I guess take advantage of those features to make this a little bit more concise. So we're cutting down maybe 3 or 4 instructions, but these maybe, once you assemble them, turn out to be many more bytes than what may be here. So once we've entered the loop, each time we call, the system call is going to trash EAX. So we have to set that up. We call the system call, it's going to be dupe2 c, 2 for the first one. And then we decrement ECX, and if EAX is not set, it's going to, well, I'm sorry, decrement is going to set the sign flag if it passes 0. So if ECX goes from 0 to -1, it's going to set the sign flag. And if the sign flag is not set, this tells it to jump, a short jump back up. And once you assemble this, it's all possession independent, so this label doesn't throw off anything once you put this exploit into play. So once you put this payload into play, I should rather say. So once you jump back up, you set back up EAX again, call the system call, you decrement it from 1 to 0, and it's going to jump back up and then do it all. It's going to decrement it from 0 to -1, and it's going to say, oh, hey, the sign flag is set, continue, don't jump back. And then you can do the exec.ve shellcode, and the connect back turns out to be shorter, less steps, and defeats these security tools that we have to prevent, attackers from hacking things. And it's just funny how the connect back actually plays out to be smaller shellcode and more powerful one. We're going to cover return to library style techniques next time, lead into ROP, and as you'll see with return to library style techniques, actually you can do a lot more with that form of exploitation than an equivalent amount of shellcode that you've written by hand, by just reusing the existing features within a binary. So it really only involves changing 2 lines of the assembly in the existing port binding shellcode. If you want to change this to connect back shellcode, and you just have to cut out listen and accept. That's serious. The 2 things that you have to change are changing the socket call here to sysconnect, and once that's successful, it's going to proceed and no longer block. I think this is cutting off at the bottom, yes. So it's cutting off the final intox 80, and it's going to proceed, and it's pretty straightforward. So the shellcode presented on this slide, minus what's cut off here at the bottom of the left column, that one instruction, is shellcode that I've used in CTFs to spawn, to connect back to me and provide a shell on that box. So that covers defeating some features of intrusion protection systems and intrusion prevention systems and firewalls and other defenses at the network and transport layer. We need to continue discussion on how to bypass application layer defenses such as web application firewalls, and perhaps also antiviruses, and etc. So we talked about the buffer restrictions and the form restrictions, and discussed how regulations in various industries mandate that companies either do code auditing or just get a web application firewall, and thus they're driven to do web application firewalls. So we talked about the buffer restrictions and the form restrictions that web application firewalls will put on a web page if it learns them or is configured to do that. And the way around that is by having your shellcode be within the ASCII printable range. And there's 2 ways to do this. Well, there's actually 2 techniques that allow you to do this: polymorphic code as well as encoding. So polymorphic code refers to any code that modifies itself. You can have shell code that adds a random amount of NOPs to itself, and that would be polymorphic code because it's modifying itself in real time, and that's so trivial to write that I've heard of instructors at various universities simply having a tiny little homework saying, go do this, and students then put on their resume, I've written polymorphic viruses, and security employers are like, wow, that's really cool, but they can't do much. So the way to defeat a ASCII only filter is you're going to have valid x86 instructions that are in the printable ASCII range. So you're going to have the standard components. In theory, you're going to have the NOP sled, and then you're going to have some way of zeroing out the registers so that you can work from a known good starting point and then perform the rest of your shellcode. However, you may not be able to perform the rest of your shellcode with that limited set, which is where encoders and decoders that work in the printable ASCII range play in. And Metasploit has a number of encoders that work with this, and I've used them with some great deal of success. And so effectively what you'd have is some NOP sled that would be printable ASCII, a way to point the processor to start running on that NOP sled, or other people call it launchpad, a way to zero out the registers, and then assembly instructions that are in the ASCII range that start decoding the rest of the payload. And once it's in memory and starts executing, the web application firewall can't view it, has no introspection at that point. So it can transform itself however it wants. So basically it decodes itself to completely normal shellcode that's going to be outside of the ASCII range in most parts. So it would be pretty insane to do it a different way and perhaps, for instance, write very complex shellcode using that tiny instruction set. And I have some slides here demonstrating just how complicated that would be just for NOPs and for zeroing things out. So the way this is done is you find some sort of algorithm that allows you to use the very limited instructions you have in this range to do some form of encoding. So these are examples of assembly instructions that map to actually valid ASCII. So push ESP maps to actually capital T in ASCII when it's assembled. Pop EAX actually maps to capital X. And if you do sub EAX and for instance 39393333, it maps to actually minus 3399. And so the sub EAX here would be minus character, and the 33 would map to 3, and 33 would map to 3, and 39 would map to 9, 39 would map to 9. So I think I had a typo here. Yeah, this is not the ASCII range. It's like 20 through 7F. So you could have anything after sub here, as long as it's how do you say, full 4 bytes if it's a 32-bit system, because if you just had sub EAX and then 20, that's going to be minus 3 bytes that aren't ASCII and then a space, because 20 is the hex value for space in ASCII. So these 3 bytes in between would be filtered out by the web application firewall, and it would drop that whole request and mitigate that attack. So given 4 bytes, however, you can do anything, you can subtract anything in the valid ASCII range, which allows you to do with the combination of AND instruction, a wide range of encoding. For instance, if you just had everything, well, it allows you to do at least a wide range of zeroing out registers and working from known goods. The easiest way to have encoding is if you have all your exploit code, all your payload in a fashion that you can add to each byte 20 and maybe more than 20, you can bump everything up to an ASCII range and then subtract it down as necessary. And you maybe have to have loop structures to work on individual bytes in some fashion if they go above it or this or that. It's really more of an art than a science here, and I'm not going to be expecting you to do this, because there are tools that do this, and they do it well. But with this, you can zero out registers, and from that, you can build any fashion of decoders. And for instance, the following ASCII, %Joan, %501:, will actually zero out EAX as the bytes in 45E4F4A and this hex value, when ANDed together, share no common bits. And so that will zero out EAX. This is just an example of one of the tricks used in this arena. So you could use all the crazy opcodes here to just build the shellcode from scratch on the stack, but the logic to do that would be just insane. Or you could do, like I already said, use it to decode the rest of the payload. So you would have the useful instructions, the sub EAX, and then whatever 4-byte combinations you like. Doing subtraction that could perhaps be doing the decoding of the rest of it. And then you increment them perhaps by your actual payload by some combination of what actually you intend to subtract it by. And that's all limited by the range of values that each byte is going to occupy once you assemble the payload, because you're going to have things that are going to be above 7F and things that are going to be below 20. So it gets tricky. And so once everything is in the printable ASCII range, you can use these instructions to decode it once you've encoded it to be in the printable ASCII range. And so, for instance, this from the book, I believe printable.s is something on the live CD for a book that provides working connect-backed shellcode or some shellcode that does networking and has been encoded in the printable ASCII range. And as you can see, this is all one ASCII string, and that would not get filtered out by such a buffer restriction from a web application firewall. So web application firewalls, even if they were provided with signatures to do this, there are almost infinite ways, given common architectures, to use the limited instructions provided in the ASCII range to do encoding and decoding. And I guess a field that's analogous here is the Turing complete Turing completeness, and the minimum amount of instructions that are required in an instruction set or by a language to be Turing complete. For instance, the programming language whitespace has, I believe, 3 different characters that are recognized for a higher level programming language. Not that anyone could seriously program something like a C program with just whitespace, but there are enthusiasts out there that insanely try to do it. But also, for instance, there was a recent article I saw that demonstrated that x86 without any registers is actually still Turing complete, which was interesting. So you really just have to know how this plays out conceptually and how web application firewalls can be mitigated, well, can be bypassed, I should rather say, and that there are tools to provide this bypass technique. And the Art of Exploitation reading covers this decently well, and Chapter 12 in Web Application Hackers Handbook is required and will likely have its topics covered on the midterm. And we'll be having a short lecture on the midterm review for next time, and I guarantee you that some of the required reading will show up on the midterm, even if it hasn't been covered in class. But I will give you specific pages to go read, so it's not well, how do I say? I was going to say so it's not unfair for all the slackers, but oh well. And that's it for class.